Today we are going to be introducing the ideal gas and the real gas concepts. In addition, we are going to be studying two special cases of an ideal gas, which are Charles' law and Boyle's law. But first off, what's an ideal gas and what's actually the relationship relating a real gas to an ideal gas? Starting with the case of an ideal gas. An ideal gas is a hypothetical gas, meaning it's a conceptual idea, and an ideal gas does not exist in nature. In addition, the molecules of an ideal gas, they do not have a definite volume or a definite mass, meaning that its molecules are considered to be massless and they do not occupy any significant volume. Moreover, there aren't any intermolecular forces that exist between its particles, meaning that the particles of an ideal gas, they do not interact with each other. And finally, the collisions that exist between the molecules of an ideal gas and the walls of the container in which they are contained, these collisions are considered to be elastic collisions, meaning that we do not have any energy loss whenever an atom or a molecule collides with the walls of a container. Now moving on to the real gas. In the case of a real gas, such gas does exist in nature. So unlike the case of an ideal gas, which is a hypothetical one, a real gas can be found in nature. Moreover, the molecules of an ideal gas, they do have a certain mass. They do have a definite mass, and therefore they do occupy a certain definite volume. In addition, the molecules of a real gas, they do interact with each other. Therefore, there are intermolecular forces that exist between them, which is not the case of an ideal gas. And finally, whenever we have a collision between the molecules of a real gas and the walls of a container, these collisions are considered to be now inelastic collisions, meaning that we do have energy loss in terms of kinetic energy whenever a molecule of real gas collides with the walls of a container. But what is actually the relationship relating real gas to an ideal gas? Like I said before, an ideal gas is a conceptual idea. It's a conceptual concept which is used in order to predict the behavior of real gases. So all real gases are going to be approximated to be ideal gases only under certain condition, which is for the real gas to exist under low density. Because at low density, the molecules of a real gas, now they are going to be far apart from each other. So the average separation between the molecules of a real gas at low density is going to be big. In addition, whenever you have a real gas at low density and therefore its molecules are far apart from each other, therefore there aren't any intermolecular forces that exist between these particles. So the forces now are negligible. And in that case, we are approximating a real gas to be an ideal gas at low density. So whenever we have a gas at low density and that can be approximated into an ideal gas, therefore that gas, it can be described in terms of the equation of state for an ideal gas. So the equation of state is an equation which is used in order to describe the state of an ideal gas, which is given as PV equal to nRT. So that equation, it signifies that the behavior of an ideal gas, it depends on a number of variables, which are the pressure and the volume, which are directly proportional to the temperature and to the number of moles, while R over here is a universal gas constant. Like I mentioned at the beginning, today we are going to be studying two special cases that are derived out of an ideal gas, which are Charles' law and Boyle's law. And these two laws, they are derived from that equation of state, which is representative of an ideal gas, PV equal to nRT. Starting with the first law, Charles' law. Charles' law states that for a fixed mass of gas at constant pressure, the volume is directly proportional to the temperature, and the equation is given as V equal to C times T, where C over here is a constant. So when we say that, we are fixing the mass of gas, meaning that we are fixing that number of moles over here, N. In addition, we are also fixing the pressure. However, we are also stating that the volume is directly proportional to the temperature. So initially we have PV equal to nRT. Whenever we say we are fixing the mass of gas, meaning we are fixing the number of moles, so we are fixing that quantity N over here. In addition, we are fixing the pressure at which that gas exists. Therefore, that equation can be written as V equal to N times R over P times T. So that term over here, N times R over P, is actually a constant, since we are fixing the number of moles and we are fixing the pressure, and R is already a fixed quantity. It's the universal gas constant. So the term N times R over P, it can be written as a constant. It can be equal to a C, which is a constant. Therefore, that equation over here becomes V equal to C times T. So that equation over here, V equal to C times T, it arises from the equation of state of an ideal gas, which is PV equal to nRT. Let's have an example which is going to show you the direct proportionality between the volume and the temperature, meaning that whenever you increase the temperature of a gas, therefore its volume is going to increase, or whenever you decrease the temperature of a certain gas, therefore its volume is going to decrease. Let's have a look at the following schematic, which consists of two beakers that are filled with water. However, the beaker on the left is actually filled with hot boiling water, and that is indicated on the thermometer as a very high temperature, while the beaker on the right side is actually filled with cool water, which is indicated on the thermometer as a very low temperature. And in each beaker we are immersing a container that is filled with air molecules. However, we have the same amount of air molecules in each container, so we are fixing the mass of gas in each container, or simply we are fixing the number of moles in each container. In addition, each container is actually equipped with a movable piston, so that piston can freely move up and down without encountering any resistance from the walls of that container. Now, before studying the effect of hot water and cool water on the air molecules, let's have a look at the following schematic, which is going to be representative of the effect of a hot environment or cool environment on the displacement of air molecules. In the following schematic, we have two balloons that contain the same amount of air molecules. However, in the first balloon, the air molecules are maintained at room temperature. So whenever the air molecules are maintained at room temperature, they are going to preserve their equilibrium position, meaning they are not going to be vibrating. And as a result of that, the air molecules are going to be occupying a very minimal volume, as we can see in the first balloon. So the average separation between the air molecules is actually too minimal, and that is because the air molecules are maintained at room temperature, and therefore they are going to be maintaining their equilibrium position. While in the second case, now we are increasing the temperature of the air molecules. So whenever we are increasing the temperature, therefore we are supplying the air molecules with a kinetic energy. In other words, we are supplying them with enough speed. In that case, the air molecules are no longer at equilibrium, but rather now they are going to be vibrating at a larger amplitude. So as we can see now, the average separation between each air molecule, it grew larger. And that is because we have increased the temperature of the air molecules, and therefore we have increased the kinetic energy of each air molecule. So they are no longer at equilibrium position. So how can that effect translates into our topic of today? So back to that schematic over here. In the first container on the right side, we have cool water, and we have a container which is filled with air molecules and immersed in that cool water. Therefore, the air molecules are going to be maintained at room temperature. So the air molecules are going to be preserving their equilibrium position, and as we can see, the average separation between each air molecule is actually too small. So the air molecules in total are going to be occupying now a lesser volume. So the volume and the temperature in that case, they are directly proportional to each other. So when we lower the temperature, therefore we are lowering the movement of the air molecules, and as a result of that, now they are occupying a lesser volume. Now moving on to the beaker on the left side, which contains hot water, boiling water. So in that case, when we immersed that container and that beaker, therefore the air molecules within that container, now they are going to have their temperature increases. But moreover, they are going to be supplied, as a result of that increase in temperature, they are going to be supplied with a kinetic energy. So now each air molecule is going to gain speed. And as a result of that, the air molecules are no longer at equilibrium, but rather they are going to be vibrating now at a larger amplitude. So they are going to be pushing upwardly on that piston in order to occupy a much bigger volume, due to that increase in temperature. So as we can see over here, the volume and the temperature, they are directly proportional to each other in both cases. In the first case, whenever we lower the temperature, therefore the movement of air molecules, it slowed down and they occupied a lesser volume. While in the second case, whenever we increase the temperature, therefore we are increasing the average kinetic energy of each air molecule. Therefore each air molecule is going to gain speed and it's going to vibrate at a larger amplitude. So the air molecules now, they are pushing on that piston upwardly in order to occupy a bigger volume as a result to that increase in temperature. And that would be the case of Charles' law, where the volume is directly proportional to the temperature while we are fixing the mass of gas and we are fixing the pressure of that gas. Now moving on to Boyle's law, which states that for a fixed mass of gas at constant temperature, the volume is inversely proportional to the pressure, P equal to K over V. So over here, in addition to fixing the mass of gas, meaning in addition to fixing the number of moles, we are also fixing the temperature of that gas. And therefore the volume, it should be inversely proportional to the pressure. And that equation over here, it also arises from the equation of state of an ideal gas. So the equation of state of an ideal gas is the following, PV equal to nRT. However, in that case, in the case of Boyle's law, in addition to fixing the number of moles N, we are also fixing the temperature of that gas. So that product N times R times T is equal to a constant, since R over here is already a constant. So N times R times T, it can be equal to a certain quantity K, which is a constant. So the equation over here becomes PV equal to K. Therefore, the pressure is equal to that constant over the volume. So from that equation, we can deduce that whenever we increase the volume which is occupied by the gas, therefore we are reducing the pressure of that gas, or whenever we decrease the volume which is occupied by that gas, therefore we are increasing the pressure of that gas. How can we prove that inverse proportionality between the pressure and the volume? Let's have a look at the following schematic, which consists of two containers that contain the same amount of air molecules. So we are fixing the mass of gas in each container. And in addition, we are also fixing the temperature in each container. However, if we look at the side of each container, we have a device which is called the manometer. The manometer is a pressure device. It's a device which is used to measure the pressure of gas. Now, in a similar manner to the previous schematic that we have seen before, each container is equipped with a movable piston. So that piston is free to move back and forth without encountering any resistance from the walls of that container. Let's start with the container down below. We can clearly see that air molecules are pushing the piston forward until they occupy the needed volume that they should be occupying under normal conditions. However, if we look at the manometer, which is registering the pressure of these air molecules, we can see that the pressure on the manometer is actually too minimal, which is expected because now the air molecules, they are left to occupy the needed volume that they need to be occupying under normal conditions without having any force exerted on them. So they are arranging themselves, they are distributing themselves in such a way to fill out the normal volume that they usually fit in. And as a result of that, whenever the volume occupied by the air molecule increases, the corresponding pressure of the air molecules is going to drop down. Now moving on to the container at the top, and as we can see now, we are pushing the piston further inside. Therefore, we are compressing the gas which is contained within that container. So when we are compressing the gas, two things are happening. First off, we are decreasing the volume that is being occupied by these molecules. And on the other hand, whenever we decrease the volume, therefore, the air molecules now are going to be striking more frequently against the walls of that container, which is going to lead to an increase in pressure. But why would that lead to an increase in pressure? Pressure is by definition, it's a continuous force which is exerted on or against an object. So pressure by definition is equal to force over area. So whenever we confine the air molecules to a much smaller volume, therefore the air molecules are going to be striking more frequently against the walls of that container. And whenever a molecule strikes against the wall, therefore the air molecule is going to be exerting a force on that wall. So the pressure and the force, they are two quantities that are directly proportional to each other. So when the force exerted by the air molecules on the walls of that container increases, therefore the pressure of these air molecules is going to increase as well. So as we can see over here, whenever we confine the air molecules to a much smaller volume, the pressure of the air molecules increased. So over here we have an inverse proportionality between the pressure and the volume that is being occupied by the air molecules, which is the main idea upon which Boyle's law is based. And that would be it for Boyle's law and Charles' law.